Hello everyone, my name is Sahar Dasani and I'm here to present our CVPR paper, Spectral State Space Model for Rotation Invariant Visual Representation Learning. As we know, a state space model process information with a global receptive field and maintain a linear scalability to map a one-dimensional function or an input sequence named xt here to an output sequence yt. They do it through a learnable hidden state. VMamba convert this one-dimensional function to a 2D function that can process visual data as well through using an SS2D module. This module reshapes an input image into a sequence of non-overlapping patches, and it will traverse these patches using four canonical direction, which is from left to right, top to bottom, right to left, and bottom to top. Um, but there are some limitation with the current state space model is that they have limited contextual awareness. They capture a relationship only between the patches that are adjacent to each other, and they are really sensitive to spatial information. The fixed traversal scan jump between foreground and background multiple times, and also they are sensitive to rotation. The sequence of image patches depends heavily on the image orientation. So to overcome this limitation, we propose a Spectral VMamba, which is a new rotation invariant visual SSM that can leverage the spectral graph theory to overcome the direction sensitivity and rotation vulnerability of existing SSMs. This is an overview of our method, which has several steps, which we're going to go through it one by one. The first module is rotational feature normalizer, which is RFN. This module will create rotation invariant patch features. It will rotate image by three predefined angles, which is four canonical direction, and it will pass them through a patchification layer. After that, it will unrotate the feature maps to the original orientation so that when we want to aggregate all of them with an element-wise max operation, the corresponding feature aggregates together. The feature map at the end of this module will go through the several spectral VMamba blocks, which can consist of three steps. First, a spectral traversal scan. This module will represent an image as a graph and then create the adjacency matrix for it. And then after that, if you compute the first m smallest eigenvector of the symmetric Laplacian using the Arnoldi algorithm, and at the end it will traverse the patches using the sequence of eigenvectors, and it will generate multiple traversal sequence. This multiple traversal sequence will go through the six block, which can process each one of them in parallel. And at the end, for merging all the traverses, we are using a spectral traversal merge, which can reorder all of them to the original format. And at the end, it will aggregate all of them to one feature. This method is rotation invariant because using RFN we produce patch features that are rotation invariant. Therefore, our spectral traversal scan is also rotation invariant because of two reasons. First is that the weighted adjacency matrix are only depends based on the distance, and the eigenspectrum remains unchanged under cyclic permutation. The results here represent that our method outperforms state-of-the-art methods on the classification task, and our method is rotation invariant. As you can see here, it can maintain a good level of accuracy compared to VMamba. And the effective receptive fields of our method represent that before and after training, it can cover a wide variety of the environment. Thank you for your attention. Please visit our GitHub and webpage of our paper.